So, good afternoon, everybody, or good morning in Brazil. We are very pleased to have a guest from Brazil, from Sao Paulo. Unfortunately, Gabriel was not able to fly to Poland, but he is virtually with us. And he will tell us something about, again, thermodynamics and, yes, applications in quantum information. Yes. So,
Okay.
Gabriel, thanks again for coming. And the screen is yours. Yes. So quantum
Oh,
Bayesian networks. Yes. And quantum thermodynamics. Okay. Thank you.
okay, great. Thank you so much for the invitation. I'm really glad to be here and to present this work. So just to introduce myself, my name is Gabriel, and I work in São Paulo in this quantum thermodynamics and quantum transport group. Um, and so the main motivation of what, oops, sorry, of what I'm going to present today is this idea of dealing with processes, not states. So that's the main message. So in quantum mechanics, we deal a lot with states and properties of states, but in thermodynamics, all thermodynamic quantities, they refer to processes. So not only a state, but a certain process. And I'm a little bit biased because I like thermodynamics a lot. So most of the applications that I'm going to talk about are thermodynamic, but I think that this is a really a deep issue in quantum mechanics and in modern quantum theory, which is to formulate theories that refer to processes, not states. And the problem with this is that in quantum systems, you have measurement invasiveness, which means that the process becomes extrinsic. It's extrinsic in the sense that a certain property that you compute doesn't depend only on the system itself and the process itself, but depends on how you measure it. So depending on how you do the experiment, you get a different physical outcome. So the quantity that you're measuring it really becomes on the dependent on the choice of the on the choices that the observer makes. And I think that's a big issue. And in quantum thermodynamics, it's really becoming a very big area of research. So what I'm going to talk about is an overview of recent work from the last 2-3 years. This was mostly done in collaboration with Eric Lutz and Kanami Kadei, both from Stuttgart. So I'll start with this paper, which is an experimental paper, which will motivate the idea. Then I'll introduce our main idea, which is this thing called the quantum Bayesian network, which was introduced in this paper here. Then we show how to use this to discuss fluctuation theorems, and also the idea of extracting these Bayesian networks using multiple copies. And finally, I'll introduce a recent application which uses these QBNs to in statistical inference, so make a connection with statistics. So this is from our first experiment, and I think that this motivates very well the kind of processes and scenarios that we'll be interested in. So here's the idea. Suppose you have a system that is hot and another system that's cold. What we expect from standard thermodynamics is that if you put them in contact, then a heat will flow from hot to cold. So there will be a heat flow from hot to cold, and in the end of the day, they will both be at a certain temperature, which is intermediate between the two. But in these two papers here, Partovi and then Jennings and Rudolph, they discuss the possibility of making these two systems interact, but as such that they start in a correlated state. So these two systems, they are locally thermal, but globally correlated. And then if you engineer these correlations, what you can actually do is you can make heat flow from cold to hot. So you can make the cold system colder and the hot system hotter. So we implemented this experimentally using nuclear magnetic resonance. And so the setup is something like this. The initial state of two qubits, so A and B, is a product state of two thermal states at different temperatures. So system A is cold, system B is hot, and this part is just a product state. But in addition, we also have a correlation term, So this correlation term it doesn't affect the reduced state. It only affects the global state. So it's just a global quantum correlation with this parameter alpha, right? Which is like a parameter that you can tune to increase or decrease the correlation between the systems. And we put them to interact. We do this using this notion of strict energy preservation. So we apply some unitary between them. So they are going to evolve like this, just unitarily. And we choose this unitary to commute with HA plus HB. This condition is associated with these resource theories of thermodynamics. And it ensures that if there are no correlations, then we'll have the expected thermodynamic behavior. So in this scenario where there are no correlations, if this is ensured, then heat will flow from hot to cold. And so now we ask what happens if we put correlations in here. And what we get is this modified second law of thermodynamics, which says that the change, so the difference in temperatures, the difference in betas, times the heat Q must be larger or equal than the change in mutual information. So the way to read this is as follows. In the uncorrelated case, we get that beta A minus beta B times Q must be larger or equal than the final mutual information, because there will be a final mutual information because they become correlated during the process, but there will not be an initial mutual information. Initially, the mutual information is 0 in this case. And so in this, this quantity is positive. And so this means that essentially Q must have the same sign as delta beta here. So the heat will flow in the same direction as delta beta. The product of these two quantities must be positive. But now if there is an initial mutual information, this delta I is going to be a difference between final minus initial. And so you see that if somehow the process consumes mutual information, if this quantity here is negative, then we can have a situation where this product here can be negative, which means that essentially heat is flowing in the opposite direction. And so this is the experimental result. This is the energy as a function of time. And so in the uncorrelated case, you see cooling, the energy goes down. In the correlated case, you see heating and the energy goes up. So essentially by using correlations, we're reversing the heat flow, the direction of heat flow. And this is being done by consuming mutual information. So you see that here in the correlated case, we reverse the heat flow by consuming this mutual information. Okay, but what's the issue about this? The issue is, how do we actually measure heat, right? So how do we go ahead and compute this heat exchange in practice? In that paper, we had to use full tomography, and that's not very satisfactory. We had to essentially know the full density matrix of the 2 qubits as a function of time to actually be able to reconstruct the heat. So ideally, we would like to measure the heat directly, right? So just like we measure heat in classical systems, that you have something that heats up or something like that, and you just measure the heat. In a certain process, the heat is going to be the change in energy of one system or the other. So if system A has a jump from an eigenstate A to an eigenstate A prime, then you associate this to heat, or the same thing from system B, right? So we would like ideally to have something like this. And the standard protocol to measure this kind of heat is what we call the 2-point measurement. So this is a very widely used concept in thermodynamics. It was introduced in this paper here, 2007. And the basic idea is to simply measure the energy measuring the energy basis, before and after the unitary. So we make a projective measurement in the energy basis of system A or system B, doesn't matter, before they interact, and then apply a unitary and then measure again. But this is the problem, actually, because we see that if the system is initially correlated, this is that state that I wrote before, you have this diagonal thermal state, and you have these correlations here, these off diagonals. But if you do a TPM, right, and you measure in the energy basis, then you're essentially going to kill these coherences. So the TPM is invasive. It would the first measurement of the TPM would actually destroy these coherences, and so it would affect the process. When we then put the system to interact with the unitary, a different process would occur because we are essentially modifying invasively the initial density matrix. So this is a big issue in thermodynamics, because we want to be able to measure heat, but we somehow have to go beyond this 2-point measurement, because the 2-point measurement, like it or not, it always introduces this extrinsic character by invasively modifying the initial state. There has been several approaches to do this. There is an older one called the operator of work. There are also approaches related to quasi-probabilities, and these can be further linked with contextuality and other interesting effects. And there is our approach, which is this quantum Bayesian network. So this is where Bayesian networks, our framework, enters. It's essentially, in a way, as a method to go beyond TPM and to avoid this kind of backaction. So here's the idea of the quantum Bayesian networks. We have a certain system, the global system. So in the previous example, this would be the global AB system. And this system is initially in an arbitrary state, which can be very coherent and so on. So you have just a generic state with eigenstates S and probabilities PS. And this global system evolves unitarily. So we apply a generic unitary to rho, which leads to a certain evolved state rho of T. And in this perspective of eigenvalues and eigenvectors, what happens is that the populations, they don't change, right? So when we apply the unitary, the populations remain the same. But what happens is that the eigenstates, they are rotated. So the eigenstate S is rotated to an eigenstate S of T, which is U of T times S. So essentially in this picture, for each eigenstate, the population of that eigenstate doesn't change with time, but the eigenvectors are rotated. And so the idea of the QBN is as follows. We consider a generic set of times. So for instance, T0 equals 0, and then sometime T1, T2, we choose some instance of time. And for each instant of time, we build this conditional probability, which is the probability of finding the system in a certain state X, given that it is in S at time T, where this X here is just any basis that we want. So given any set of bases we want, we build a conditional probability, which is what one would obtain if we were to measure the system in the basis X, given that it is in this state S of T. And so now the Bayesian network idea is that for a given path, X0, X1, X2, and so on, we build a probability distribution, which is just, we sum over all initial states PS, and then just this chain of conditional probabilities, the conditional probability that it's in X0, given that at time 0, it's in S0, then X1, S1, and so on. Sorry, there is actually, here should be like this, right? So you can have a generic chain, generic network, by just building these probabilities. So that's how one would go about and build the Bayesian network. So the logic is a little bit like this. In the language of Markov chains, the system would be what we call the hidden layer. So it's just kind of something that evolves, and this hidden layer we don't have much access to. What we have access to is that for each instant of time, we want to have access to a certain probability of finding the system in this state, which we call the visible layer. And so the system is just evolving from S to S1 to S2 to S3 and so on. And at each instant of time, we just compute the associated conditional probabilities. So what's the interpretation of this and the value of this? So one main advantage is that it produces always a valid, strictly non-negative probability distribution. I write this because there are other approaches which introduce quasi-probabilities and which are probabilities that can be negative. Here, there is no such issue, so it's always a valid probability distribution. If we marginalize over any state, we always get something which has no backaction. I will illustrate this through some examples in a second. And even though this seems a little bit like an artificial probability distribution, we actually showed that this can be associated to the actual outcomes of an experiment, but it will involve multiple copies of the system. So I'll talk about this in a second. And just to give an idea of how this works, going back to that heat exchange example, this path x0, x1, x2, it can be absolutely general. I mean, this choice of basis is can be anything we want. So one thing we can do is we can have like a global A-B system which is evolving, and we can look at the probabilities of finding the system in these local bases. So we have this initial state rho AB, which we assume is correlated. So this is, you know, some correlated state, and you have this S, which are eigenstates which live on like the global Hilbert space of A and B. And then as this system evolves, we ask for the probability of finding the system in these local bases, system A in basis A, system B in basis B. And so now we can use this to actually construct the heat distribution. So for instance, we can have the Bayesian network of A0, B0, A1, B1, and we can just define heat now in the way we're used to as just the change in energy of the system, A, or of the system B. And then the distribution of heat is just, you know, we sum over all possible trajectories, A0, B0, A1, B1, such that the heat Q is given by this difference. And so this allows us to construct a distribution of heat which has no backaction. So now that we can find the full statistics of heat, and there is no backaction involved. Okay, so let's see how this compares with the 2-point measurement. So let's consider in more detail this heat exchange QBN. So this is something that involves 2 steps. And so the full Bayesian network would look something like this. We sum over all initial eigenstates of the system with weights PS. And then we have these transition probabilities of A0, B0 at time 0, A1, B1 at time 1. So these are given by just the this is flipped. This guy is this guy, and this guy is this guy. I flipped it around, but okay. So this is just the probability of finding the system in the local states A0, B0, given that it's globally in S. And this one is the probability of finding it in A1, B1, given that it's globally on this evolved state U times S. And for instance, let's see what happens if we marginalize over A0, B0. So we just sum this formula over A0, B0. And if we do that, this term just vanishes. So we just throw away this term. For any S, this probability just vanishes. And what we get is that the probability of finding the system in A1, B1 is just given by this formula, which is just a familiar formula. It's, you know, the sandwich of the final states given the evolved state. So there is no backaction here. And now let's see what happens in the TPM. So the big difference in the TPM probability distribution would be this term versus this term. So you see, the whole idea of the Bayesian network is that there is no backaction. So here we have the transition probability from A0, B0, and S, but we don't assume that the system collapses to A0, B0. In the TPM, we assume that it does. We actually do the measurement. And so here, instead of looking at the state S evolved in time, we have to look at the state A0, B0 evolved in time. And if we now marginalize over A0, B0, we get something different. So instead of having just the sandwich of U rho U, we have the sandwich of U D of rho times U, where this D of rho is the dephased rho, is the state rho dephased in the eigenstates in the initial eigenstates. So this shows the invasiveness of the TPM. In the TPM, even if we are only interested in the final state, the result will be affected by the measurement we did in the initial state. Whereas in the Bayesian network, this is completely independent. Anything about the initial state does not affect future states. Okay, so what are some of the consequences of these Bayesian networks? The first nice consequence that we find is in the existence of fluctuation theorems. So fluctuation theorems is something that people in thermodynamics really like, because they reflect these fundamental symmetries about thermodynamic processes, which are related to the second law of thermodynamics. It's in a sense a generalization of the second law. So we considered the general quantum Bayesian network for choose that process, but I'm not going to sum over S. So I'm going to consider the joint probability of A0, B0, A1, B1, and also S, which is just given by this. And we also define a reverse trajectory, which is essentially instead of going from A0 times 0 to A1, B1 at time 1, it's the other way around. So we start in A1, B1, and then you go to A0, B0. And essentially the evolution, so these P bars is the same kind of transition probability, but with the time reversed unitary. So instead of using mu, we use the reversed unitary. And so these fluctuation theorems, they essentially are a relation between these forward distributions and these backward distributions. And in this case, what we find is that the ratio is given by this formula. And the interpretation of the many terms here is as follows. So here is the heat, delta beta times Q. And then we have two terms associated to mutual information. So this is the initial mutual information and the final mutual information. They are given by these formulas here, which is a little bit confusing in terms of symbol, but it's just easier to think about this as a stochastic mutual information. So it's just the stochastic version of the mutual information. Then we have these two terms here, sigma A, sigma B, which are related to relative entropies of the two systems. So they are essentially related to how the system evolves, how far each system is from its initial local state. I forgot to write it down here. Apologies. This calligraphic P of A1 is just A1 rho AB, sorry, rho A prime A1. So it's just the final state of the qubit, the probability of finding the each subsystem in its final state. So in the evolved final state. And finally, we have this term gamma here, which is associated to the transition probability. So it's associated to this ratio of dynamical terms and transition probabilities. But what is interesting about this is that this kind of fluctuation theorem implies this, what we call an integral FT, or a non-equilibrium equality, which is that the expectation value of these quantities is always equal to 1. And so this is a generalization of the fluctuation theorem to include these informational terms. And what is nice about this is that many of these quantities actually satisfy individual fluctuation theorems. So the mutual informations, for instance, and the relative entropies, and this dynamical term gamma, they satisfy these individual fluctuation theorems, which is a nice feature. And moreover, we can also mutual information into a classical term and a quantum discord term. So there's a term associated to classical information and a term associated to coherent information. And these two guys by themselves also satisfy fluctuation theorems. So we actually show this here. This is an experimental result from our second experimental paper, which shows the expected value of these quantities in the same qubit example that I showed before. So the nuclear magnetic resonance experiment that we did. We see that all quantities are very, very close to 1. These two quantities, the sigma A and sigma B, they're a little bit off, but this is within the error bar. We didn't include the error bars here, but if we do include them, then you see that this quantity is still very close to 1, right? So it's still pretty close. Okay.
I'm
and
sorry.
yeah,
May I have a look again at this last picture?
this
Yes.
one.
So
Yeah.
yes. So in fact, the horizontal axis. What is plotted at the horizontal axis? Different
Right.
quantity.
Yeah. So each point is just a different, completely different quantity. It's not a.
Okay. So in fact, it's not an axis, but just a configuration of different results.
Yeah.
Composition
Yeah.
of results. Okay. So there's
Yeah.
no
Exactly.
kind of order, pre-order.
No, there is no order. Yeah. So it's
Okay.
just different
Okay.
quantities. It was just the best way we found to just, because there are many equalities we needed
Yes.
to plot,
Sure.
and
Sure.
we
Sure.
felt that
Sure.
this was the good way.
Okay. And two of them are distinguished because they are kind of this identity. Yes.
Yeah, but this is an experimental feature.
Okay.
Theoretically, we would predict one, but this is due to experimental error. These two quantities, they're more sensitive to errors than the
Yeah.
others.
By the way, and what kind of experiment those data represent?
Yeah, so this is the same experiment, same setup as this one. So it's essentially a nuclear magnetic resonance where you have like these chloroform molecules that have two spins, so just two qubits prepared in this kind of state. So it's the same kind of experimental setup. We do it with magnetic NMR.
And still two qubit system.
Two qubit system.
Okay.
Yeah.
Okay. Thank you.
Yep.
Gabriel, can I ask you something?
Of course.
Yes, there's a fluctuation theorem for heat, which I think it's called by Jarzynski-Wojcik, right?
Yeah.
It relates the ratio between the probability of the forward process with the backward process. And this one that you got is not exactly this Jarzynski-Wojcik fluctuation theorem, right?
Perfect.
And this is because the systems are correlated, or the scenario is different?
So thank you for the question, because this is the next slide. Yeah.
Okay.
Yeah, perfect. So that's exactly the idea. This is actually shown here. Yeah. So this is again from the experiment. We just plot the forward and the backward heat distribution. These two plots are uncorrelated. These two plots are correlated. So the way we read these plots is that heat here can actually take three values only. So we just have the probabilities of three possibilities for the heat as a function of time. And this is the forward, this is the backward. So if they are uncorrelated, so more generally, there is what we find in our paper is that the ratio between the forward and the backward trajectories is this exponential of delta beta q divided by this new function psi, which is a kind of strange function of heat, weirdly defined. But this is associated to correlation. So this psi of q is 1 when they are uncorrelated, and it's different from 1 when they are correlated. So if they are uncorrelated, what we get, so in the uncorrelated case, this term would be 1. And so if we compute the logarithm of this, so if we compute log of p forward of q divided by p reversed of minus q, then this would be just delta beta times q. So it would be a straight line in q. So the log would be a straight line. And this is actually plotted here. So the uncorrelated case is the green curve. I know this isn't fantastic because there are only 3 points, but if you look at this point, then this, and then this, there is a straight line between them. But as soon as there are correlations, we get this function. So this log is no longer a straight line. And so the purple curve here, you see that from here to here is not the same slope as from here to here. There's like a kink. It's a little bit like shifted. And so these violations of linearity are an indication of correlation. If they were uncorrelated, you would get a straight line. But if they're correlated, you get something which is a nonlinear function. Of course, it would be great to have more points here so we could actually see, this nonlinearity. But this, in this case, unfortunately, this is the best we can do. Yeah. Does that clarify your question, Alexander? So we recover Jarzynski-Wojcik in the limit of uncorrelated case, but we show violations of it in the correlated case.
Yes, thanks.
Cool. Okay. Next, I want to talk about how we can actually extract these Bayesian networks from multiple copies. So as I've shown you, these QBNs, they have nice properties. but they seem to be a little bit artificial. In fact, in our experiment, we reconstructed them from full tomography. So we just had full tomography, and we have everything, and then we just rebuild these Bayesian networks. So it's a little bit frustrating in that sense, because we're not really, when you think about a probability distribution, we like to associate it to the outcome of a certain experiment. In our case, it was not like that. We had to do full tomography and then just reconstruct this artificial probability distribution. So it would be great if we could link QBNs directly with the outcomes of an experiment. Using just a single system, this is impossible. So if you just have a single system and we want to do some measurement on it, this is impossible, because of course, I mean, it's kind of the whole point of the QBN, because if you have a single system, any measurement we do would have a back action on that system. And so we wouldn't really be doing a QBN, we would be doing the 2-point measurement scheme. So this wouldn't solve anything. But what we have recently shown is that if one has access to multiple identical copies, you can actually do an experiment on multiple copies of the system. And this will lead to the QBN as being directly associated to the outcomes of an experiment. So this is what I'm going to show next. So the trick is post-selection. Let's consider for concreteness a 2-point QBN. So I'm going to simplify my notation a little bit. I'm just going to consider 2 states, x0, x1, and the QBN is just sum over all initial states PS, and then the transition probability is x0, s0, x1, s1. So this is x0, s0, and this is x1, s1. Okay, so how do we do this? It's actually quite simple. Suppose we have 2 copies of the initial state of the system. So let me just remind you, the initial state was PS, SS, right? So suppose we have two identical copies. And what we do is we first measure them on their eigenbasis S. So we do a projective measurement on both of them. And now we post-select. So we're going to get many outcomes, and we throw away all those systems where the copies are in different states. So whenever we get an outcome that one copy is in a different state than the other, we throw it away. And we just post-select those states where S prime is the same as S. And now on these states, we apply a POVM. So we apply this measurement where in the first copy, we measure on X0, and in the second copy, we measure on UX1. So a product of projective measurements. And then the outcomes are exactly this QBN. So that's what we show. If you do post-selection and then a product POVM, the outcomes are exactly this. And I'll illustrate this in a second with a concrete example. So this is very nice because post-selection is not too bad, right? I mean, you just have to do a bunch of measurements and throw away a lot of data and just keep the data that you want. So with post-selection, we can actually do this in a scenario that is very similar to the original TPM, but here we have to always work with copies of the system. So always work with 2 copies of the system. And if we do that, we can get these measurement outcomes. So let me illustrate this through a concrete example, which is the work distribution in coherent processes. So this is a different configuration than the one we were talking before. And part of the idea is to show how Bayesian networks can be used for many different thermodynamic processes. So before we had 2 systems, A and B, which were exchanging heat. Now we just consider one system isolated, and we do work on it. So essentially, we just have a system in a state rho. We apply some unitary on it, which leads to rho prime. And this unitary may be associated to some work. So the Hamiltonian may actually change. So there's an initial Hamiltonian with initial energy eigenvalues and energy eigenvectors. And this may change to some final Hamiltonian HS prime. So we assume that this unitary is associated to this work protocol. If one wishes to be more concrete, we can maybe write U as being the time ordering of the exponential of minus I, the integral from 0 to some time tau of some HS of t dt, something like that. But we don't actually have to do this right now. we just assume that, whatever is this time-dependent Hamiltonian, it just generates some unitary. So what we need is just the big unitary and the initial and final Hamiltonians. We don't need to understand like how the Hamiltonian changes in time or something like that. So that is all encoded in the unitary U. And so in this case, there is no heat, so no heat involved. And so the average work is just the change in energy. So we have initial state, initial Hamiltonian, final state, final Hamiltonian. Whatever is the average energy changes, this must be associated to work. And the work is because, there is this unitary which is generating some time-dependent Hamiltonian. And so there's like an external agent that is doing work here. But if we want to measure this work, like how can we actually extract this W, right? This WC, it's clearly a function of the process, not the state. It depends on 2 points, right? So if we want to measure this W, we would have to do a measurement before and after applying the unitary, which would be the TPM, right? And if the system is initially coherent, so if essentially this basis here is measurement would be invasive. So in fact, the TPM, it would actually produce an average work, which is not the average work that we would expect physically, right? So this is the natural definition of average work. But if we do a TPM, we get something else. We get because of the initial measurement. Okay, but if we do a QBN, then we have here this transition probability from S to Ni, but we don't assume that there is a backaction. So here what enters is S. And if we now use this to build the work distribution, we get the correct average work. So the Bayesian network preserves the average work. So it gives the correct value for the average work. And the reason why I'm talking about work is that there is an interesting connection with a now famous paper by Marty Perarnau-Loblé and other authors, which is what they call a no-go theorem for work. So what they do in this paper is essentially they propose the following question. Can we actually devise a POVM, J of W, such that the work distribution is directly the outcome of this POVM? So we have a general POVM, and the outcomes of this is directly the work distribution in thermodynamics. And the question is if this can be done satisfying 2 criteria. First, it should give the correct average work. So one has to devise this in a way that provides that yields the correct average for the work. And 2, it must reduce to the TPM when the system is initially incoherent. So in the case where there are no coherences present, it should reduce to the standard TPM, but otherwise it should always give the correct work distribution. And what they show is that this is impossible. So they demonstrate that one cannot do this. When it's impossible to find a POVM that does both things. But that's because one is working with a single copy of the system. If we work with 2 copies, like in the Bayesian network, we can actually do this. So with the Bayesian network, we can actually build this POVM. I write it here for completeness. And with this POVM, we can actually satisfy both of these properties. So by using 2 copies of a quantum system, we can actually violate this no-go theorem. We can go beyond this no-go theorem. There is a caveat, which I must talk about, which is the question of what may J of W depend on, right? So there is, in this no-go paper, there's this interesting discussion of what would be physically reasonable for a POVM to depend on. And what they argue is that the POVM shouldn't depend on the state row itself. So you see that the idea is that for any state row, you would have the same POVM. And this is not the case here. In our case, you see that there is this PS and this S, which are properties of the initial state. So our P of M does depend on the state rho. And so in this sense, it's really not like a full violation of the no-go because we still have this caveat, but still it's a partial violation, so to speak. Okay, and then finally, I want to talk about some recent work that I have done with a student of mine, which uses these Bayesian networks to study a problem in statistical inference. And this is something I'm kind of very interested right now, this connection with inference. And so what we do is we studied what is called a predictor of work. This concept of predictor, for some reason, is not so widely used in physics, but in statistics, people like it a lot. So here's a simple example. Suppose X is a random variable, which denotes the grades of a student in a college admission exam. So the grade of a given student. And Y is the grade of that student in the first year physics course, right? So then the idea is these two things, they're probably correlated, right? So a student that got a high grade in the admission exam has a high probability of getting a high grade in the first year physics exam. So the idea of a predictor is to build a function G of X, which provides the best prediction for Y given X. So, you know, what's the best guess that one can, suppose that you know that a student got a 9 on the college admission exam. What is the best prediction that you can make about what will be that person's grade in the first year physics course? So that's the idea of prediction. And this notion of best is essentially we're trying to minimize this mean squared error. So we want to minimize the distance between this function that we're trying to predict and the actual outcome. So in our case, what we propose to do is to use this in the following context. We have a system coupled to a BAF, right? And the BAF we assume is incoherent, so we can do TPM on the BAF. We can do TPM here, but the system is a coherent quantum system, and we don't want to measure it. We don't want to directly measure the system and apply a TPM. So then the question is, suppose we measure the BAF and we get some heat from this interaction with the system. What is the best prediction that we can make about the work given the outcomes of the heat that we got here? So it's a question in statistical inference. We get some heat from the BAF, and we want to ask what's the best prediction we can make about the work involved. And so the idea is that here we're going to mix Bayesian networks with TPM. We do the TPM on the BAF, but we do a Bayesian network in the system. And so essentially we have this probability NM mu prime, where N and M are the energy eigenstates of the system, and mu prime are the eigenstates of the BAF. So there is like a BAF Hamiltonian, which is sum over mu, E mu, something like this. And the BAF is thermal, so there are also these thermal probabilities here, Q mu. And so what we want to do is we want to minimize the mean squared error between this predictor, calligraphic W here, and this thing which would be the actual work, which is essentially the difference between energy in the system and energy in the BAF. So it's the from the first law of thermodynamics, this would be the average work. And what we do is we find a formula for this predictor, which is written solely in terms of the cross operators of the system. So the interaction, the fact that we measure the BAF generates a set of cross operators, like a quantum channel for the system. And each trajectory, like mu prime, which would be a trajectory for the system, occurs with this probability P of mu prime. And we find the following formula, which is like a closed formula for the optimal predictor. So this is the predictor which optimizes the mean squared error. And we think this is a very nice result because it provides a very easy way of predicting work based only on the cross operators. So if one has access to the kind of cross operators that's associated to a process, you can make predictions about the work. And we thought that this is very nice. So let me show you an example. this kind of idea that I'm talking about has actually been studied experimentally already. So there's this famous paper by Jukka Pekkala's group, which uses a calorimetric method to measure work from outcomes of heat. So the idea is that you have some heat, and you want to, from that heat, measure the work associated to a process. And so one thing one can do to facilitate things is to assume that the unitary is split in two. So first you do some work. First oh, sorry, this is wrong. This is I of the environment. Apologies. So the idea is that first you do some work only on the system and nothing on the environment. And then you do some heat exchange between them. So we work with a minimal model, which just consider a qubit, which has the same initial and final Hamiltonian, and we perform work by just applying sigma x. This would be like the simplest kind of model we can cook up. And then we assume that the system, that the bath is also a qubit in some thermal state. So you have some thermal population F and just a simple Hamiltonian for the bath. And the interaction is just a swap. So the system and the bath, they just swap states. And we assume that the initial state of the system is this, so it can have coherence, right? So there is this theta, which represents the coherence, and this S, which represents how mixed the state is. And so here's a table of values. And this is the last, essentially the last slide that I have. And I wanted to just explain a little bit this idea. So suppose we have a situation where there are transitions such that the work is plus omega, like for instance, this second line here. So the actual work that was involved was omega. And in this case, the heat involved in this set of trajectories was also omega. And so the predictor makes the right guess. From this heat, the predictor gets it right that the work involved was omega. And this is for incoherent systems. So this is incoherent processes. Incoherent. But sometimes the predictor doesn't get much. So for instance, in this first line, the work involved was minus omega, but there was no heat. So the experiment didn't detect any heat. But still, the predictor can cook up a function, which is the prediction of work. It's not the actual work, so the prediction is not perfect, but it's still a prediction, right? And so that's kind of the idea. You have the actual work involved, and you have what would be a prediction of this work. And sometimes, in some cases, this prediction can be perfect, but usually it's not exactly perfect. And if one now goes to coherent systems, then it becomes a little bit more complicated. The predicted work, so that would be kind of the idea of predicting work from measurements of heat. So conclusion and outlook. What I've talked about is this idea of quantum Bayesian networks. They are associated with multi-time quantities. So whenever you have anything that depends on a process that depends on multiple times, and you want to study these things statistically without measurement backaction, then quantum Bayesian networks are a nice feature. And this is particularly important for coherent systems and processes. But what I've also shown is that this is directly associated to experiments on multiple copies. And it has a very meaningful thermodynamic interpretation, in particular in terms of these fluctuation theorems. And as the last part, I also discussed how we can use this to construct this prediction, which is an estimation scheme. So connect directly with statistical inference. And as an outlook, we're now looking for potential applications. So we're currently studying continuous time engines and quantum transport. So this is one example of the type of system we're working on. This is a 3-level heat engine where there's some coherence between these 2 levels. So there's this Wi-Fi symbol here, which means there's some coherence here. And so the idea would be to predict work in this engine from measuring the heat. But since we have these estimation schemes, we're also looking for applications of this in beyond thermodynamics, in particular in quantum metrology. And also others, I don't know if anyone has any suggestions, I would love to hear. So that's pretty much it. This is the list of references that I mentioned. This is my website if someone is interested in learning more. And thank you very, very much for your presence.
Yes, thank you very much. Thank you, Gabriel, for visiting us and for your nice talk. Before discussion, I will only make some more personal remarks. So maybe you know that Chris Jarzyński understands Polish, even though he works in US. And Daniel Wójcik, he used to work in Warsaw, then he was a postdoc in US. And I'm very pleased that you quoted the paper. So now Daniel is back in Poland and he turned more to biological physics, but he's doing very fine. Yes.
Oh, that's very interesting. I didn't know.
Yeah, so yes, and Daniel also was delivering his seminars during this chaos and information seminar many years ago. Yes, yes. So he's our like colleague.
Cool.
Yes,
I didn't know that.
good, good. So let us now open the talk for discussion. Any questions, comments?
So
Please.
I was curious here, Gabriel, and first, thank you very much for the talk. It was very nice. I was curious here in the second example that you gave, the example that you were interested to compute the work distribution, if you got a fluctuation theorem, which is more general than the Crookes theorem, because now the system is in a coherent state.
That's actually a very good point. We didn't really do this yet. I think one of Eric's students is working on this, but yeah, that's something we didn't look at. So that definitely one can make a fluctuation theorem. It would be likely similar to the one I showed before for heat, but some difference I have to still understand. So I think one of Eric's students working on this, but so far we haven't yet.
I see. And is there any
Sorry. So if we want to estimate the work, essentially we associate the work with the application of some unitary. So we assume that there was some process that prepared the state in some state, and then the work is just associated to the application of this U. Now, if we want to actually use U to generate coherence, then this will also be part of the work. And if the system is initially incoherent, then actually the TPM gives the same as the Bayesian network. So if initially this system rho is incoherent in this basis of the initial Hamiltonian, then it doesn't matter if one does TPM or Bayesian network, it's independent. The real use of Bayesian network is exactly when the system is kind of incompatible with the Hamiltonian.
I see. Thanks.
So Kamil wrote a few words about the nice talk, but he had to leave for another meeting. Yes, so best regards from Kamil. Are there any other questions and comments? Well, so let me ask another question concerning, let's say, experiments. Of course, for physicists, it's nice if you can, for theoretical physicists, make any connection to experiments. So do you have any direct contacts with experimentalists, or do you know somebody who does those experiments yourself?
Yeah. So this experiment here, these NMR experiments, they were done by a group in Rio de Janeiro on this nuclear magnetic resonance. So we have a couple of experiments with them and also working on a few others.
So who is the boss of this group in Rio de Janeiro?
So the head of the groups are Yes, yes. He is originally from Brazil. Yeah.
Okay, I see. Good. So, Gabriel, thanks again for coming. And